Hello, good morning. My name is Abdurrahman Zahid, and today I'm presenting my project, which is object detection application. And I've done this project under the supervision of Mo Hassan. So my first slide is about introduction. Uh, this project is about real-time vehicle detection that is uh, built using a model called YOLO 5 version model. This project addressed the growing needs for real-time vehicles and vehicle directions in urban environments, especially for application like smart cities, traffic monitoring, and autonomous vehicles. And the next slide is of about problem statement and objectives. In urban areas, uh, face challenges like low lighting conditions, high traffic density, and the need for the real-time detection. So the object detection vehicle is about real-time detection of the objects. My project aims to build a system that is uh, highly accurate and achieve up to 140 FPS speed and developable on low devices like Jetson Nano, and Raspberry Pi. So the next slide is about model selection. Uh, while I was building my model and planning to build the model, I looked at older methods like HOG with SEM, which is Sport Vector Machine, and other deep learning models like Foster RCNN and SSD. But I choose YOLO version 5 model because uh, it is very fast and still accurate. It works in low lightning conditions, and it is faster and detect real time, and it is able to detect real time detections. It detects vehicles in just one step, which makes it perfect for real time use. It can process 140 images every second. And the next slide is about methodology. Uh, I use a dataset of over 50,000 images, 51,000 images collected from RoboFlow source. Uh, the datasets collected from this source is already in the format of YOLO version 5 format, so we don't need to manually change the data or update the data to meet the requirements for our model. So it's a time saving. Uh, Also, augmentation using techniques like rotation, scaling, uh, noise injections, pre-processing include resizing and normalizations. The model was trained using transfer learning, hyperparameter tuning by configuring the parameters and tested with the OpenCV integration for real-time detector. The next slide is about implementation and result. Uh, by implementing this model and after training, the model achieved 78.3% mean average precision and 140 FPS on RTX 3080. Uh, in comparison, um, it outperformed SSD and faster RCNN in terms of speed while maintaining competitive accuracy. The system handle different conditions like urban traffic, parking lots, and even some bad weathers as well. My next slide is about this to show the model training code and the validation output. So here it is. And the next slide is about Ethical consideration. While training my data, I used only public datasets that don't include personal information to keep people's privacy safe. I also use different types of images while training my model. For example, from various angles, different sizes, low lighting to make the model fair or works good in these conditions. This system is made for the safe purpose like checking traffic, uh, monitoring the traffic, and not for spying on people's or to leak the privacy for the people's. The next slide is about project management and agile methodology. For my project, I used development approach, which is an iterative approach. It is because my project is about to detect the real-time detection, so it needs new data, new changes to get the high accuracy. So we can make changes with getting the feedbacks from the outputs in iterations. So I followed an agile development approach, which is iterative approach. Uh, and then high-end GPUs were used for training, while edge deployment was tested on, as I told you before, Jetson Nano and Raspberry Pi. Key risks like bias, hardware limitations, and overfittings were identified and solved early. And the next slide is about future work in conclusion. In the future, it will be improved by using a vision transformer to better detect small cars. The vision transformer is for like small objects to detect accurately, and then add more car images in different conditions like extreme weather conditions, rain, fog, and making the model faster and more efficient on low power devices uh, using tools like a TensorRT and model pruning. So these are all about my project. Thank you so much. In this part of video, I will show my project where I build my model. So first of all, first of all, I use a Google Colab for my project. So in the first piece of code, I set the environment by installing the RoboFlow and Ultralytic for YOLO model, and I install the YOLO model from GitHub into my local computer and install its tools or libraries that needs for YOLO model. And in the next part, I get import the RoboFlow library and get the access using the API key to get the project and dataset for my model. So I download the version 2 model from this workspace and the project called vehicle QOX2V. This is for installing the libraries that we're gonna use in our code, like Seaborn, Matplotlib, OpenCV to read the image files, uh, sorry, Pillow files that read the image files, Seaborn for making charts, uh, so on. And in this part, I import all of these libraries. YML file is for about YOLO model. In this part, uh, I set the data path and open the YML file to read the information and print all the names of the classes that inside the data YML file. The next part is about data basic structure. So in my data set, there are three sets of data: train, valid, and test. So I count all the images and label files and print them on the output to show how many images files we have and how many labels files in train sets, same as for valid and test. And the next part is about object detection in the dataset. So in this, I made an empty list and make a loop that work for each split, test, valid, and train. It checks label files and corresponding their images files. If exist, then open the image and read its size. Uh, if the label file exists corresponding to the image, then open the file, a label file, and read its lines. Each line represents one object, uh, and each line has five parts: a class ID, like which class it from, truck, car, bus, and then X center, Y center, and width and height. This all code is about just to analyze how many objects. Oh, and then in this part, class distribution is just the graphical representation of my data set, uh, how many classes I have and how many data set we have, like how many rows in cars, how many rows in small trucks, and so on. In the next part, it's also about visualization. It shows how many data set, uh, how many like cars in our train set, how many cars in our test set and valid set as well. It is in the stack form with different colors representation. Visualization sample image with bbox is to make a bounding box around the image. So in this code, I take the sample image and change its color from BGR to RGB so that's easy to understand. And then I read the a sample image file, a sample image label file, and check if each line has five parts. If it's then count the class ID, X center, Y center, uh, top left corner, bottom right corner to draw a bounding box and give the color to the bounding box and names for the class. So here is the output. Advanced statistics is just about how many, in this code I calculate how many average uh, objects per image and what's the average size of classes for bus, truck, car, and aspect ratios, how many big, tall, what's the mean, standard deviation, and so on. Calculate the things for just static advanced statistics. And then I check, it's a data health check. It checks uh, image files and their label files exist. If not, then it prints missing label files. If both are exist but the label file is empty, then it reads the file, and if it's empty, then it uh, shows that how many empty label files in train set, value set, and test set. Now we are training our YOLO model. So I set path and then print all the files inside the dataset. So it shows how many train samples, value sample, and test sets. So yeah, so it's making the dictionary for data YML file and print that if to check configuration parameters. Here is configuration my model according to my need, and then this training part is for training the your training script to train the model. It's for evaluating model, and this is for download our project model that we made. This is the best model to in our local PC, and this is to import the model from our local PC to test our dataset. So here is the test image, the testing phase. If I change the image and check the output, how like this is our output. It tells us about accuracy, and that's all about my project. Thank you so much.